So now we're moving into our third chapter, which is our design methods. Okay. So the goal of the structural design is to determine the number, material, composition, and thickness of the different layers within a pavement structure required to accommodate a given load regime. So this includes the surface course as well as the underlying base or sub-base layers. This section is focused on the structural design of a new pavement. The structural design and rehabilitation is covered in maintenance and rehabilitation. So this is course will just talk about new pavements. I'm not going to talk about maintenance and rehabilitation. That will be a course on its own. So structural design is mainly concerned with determining the appropriate layer thickness and composition. So calculations are chiefly concerned with the traffic load stresses and other environmental related stresses such as temperature are accounted for in the mix design for the asphalt binder selection. The principal method of the structural design in use today for the simplest goes from the simplest to the most complex design catalogs, empirical and mechanistic empirical, which is what we will touch on. So we'll start with talking about design catalogs because they're the most common and they're the ones that are most in practice. So the simplest approach to hot mix asphalt pavement structural design involves selecting a predetermined design from a catalog. Typically, the design catalogs contain a list of common loading, environment, and service regimes, and corresponding to a recommended pavement structure from the state or local agencies, often including them in their design manual. So each municipality or a council or a district council or a state will have its own catalog and or a design manual, so that you can just, if this level of service for this road, it's a level surface A, or is it an arterial road? So an arterial road, these are the layers you need, and depending on the level of service, you can just select and use that design. Also depending on within the range of traffic, so they'll give you parameters. What was the traffic for this traffic? And it's an arterial road. You need to have these layers. If it's clay, you might need to have this, and then you use those catalogs for your design. So that's fairly simple. The pavement designs within these catalogs can be based on a number of different design methods, ranging from mechanistic empirical to historical experience. When using a design catalog, it's important to be aware of the author's assumptions and design procedures. So yeah, so you shouldn't just go into a design and just pick. It's not lucky dip. You must understand why those parameters exist, because as an engineer, you are liable and you need to understand what you're doing, so that when you're questioned or when you are brought to task, you can show that you were not negligent. So it's very important. Risk is very important. So you must always try and mitigate risk as a civil engineer. So often, the required level of design does not warrant the use of advanced equations or models. For instance, a local residential street subject to only a few heavy loads per week, like a school bus or a garbage truck, or maybe when you're moving in and out, like your moving truck, it doesn't warrant, the expense and time of mechanistic empirical design approach. However, some government agencies and many private owners do not have specified standard pavement structural designs. So here are just some South African Road Agency engineering Bibles. So you can see there's the TRH4. So it's for structural design of flexible pavement for interurban and rural roads. And then you can see there's the UTG. So that's for structural design of segmental block pavements. So this one is for block pavers. And then you can see here there's the TRH16. So this one has traffic loading for pavements and rehabilitation. So this one is for rehabilitation. And this is an excerpt from the TRH4. So as I was saying, depending on your road category, like the level of service, right, and your traffic. So this would be your traffic load, right? You can then go pick. Okay, so you can see my road service, for example, it's a level of service B, right? And it also depends on the region, as I was saying. So it depends on the environment. So this is for a moderate or dry region. So that would be your Johannesburg, Pretoria, Limpopo, up there, where it's considered a dry region. and in this guide there's a map to show you where in South Africa where they consider dry region, and you can see the assumptions. So that capacity is 80 kilonewtons per axle lane. The assumption, so these are the assumptions we're talking about that you need to, and this assumption is you're going to be having a granular base. So then for a level of surface B and your ES3, so your E80s are 1.0 to 3.0 times 10 to the power 6. These are your E80s, your loads. Then you can see here it's a category B, so you have a choice. You can either take the S.30A, so that's asphalt, 150 for your G3 material and 150 for your G5 material, or you can have a C4, so that's going to be stabilized. So all these codes for these aggregates are in the design code to let you know what they are, but I didn't want to go too much into that. I will have a separate course on how to design a pavement using these guides. But so this is just an introduction on everything. So I'm trying to just wrap up everything in one big course so that in my other courses, I can start breaking down each of these design methods separately. Moving on from that, so the ASHTO guides are the ones that are used in Australia and New Zealand, which is where I'm currently practicing. So this is the guide to pavement technology part 2. So this is for pavement structural design. These guides are free. All the guides that I showed you guys are free. They're free. You can download them online. They're readily available. I think for the ASHTO, you just need to create an account with them, and then you can download it for free. So this is a typical example. So this chart is a typical example that I cut out from the design manual. So what you'd have here is your CRB, your California bearing ratio, right? So having your California bearing ratio, right? You find your California bearing ratio using a DCP test. So when you find your California bearing ratio from your DCP test, let's say you found a California bearing ratio of 4, right? California bearing ratio of 4, you have your ESA. So that's your design traffic that you've calculated based on a traffic count. Or there's an app in New Zealand where it'll tell you what's the vehicles per day. You know, so that's the daily traffic. There's an app that'll tell you for this road. So then that'll actually, you know, it gives you that some councils, they have done traffic counts and they know what the average vehicles per day are for certain roads. So if you are lucky enough that you're designing for one of those roads, you can just use that app. Look, you don't have to really have a traffic count, which saves you a lot of time and a lot of money. Also, it can depend on the zoning. So here there are different residential zones. So typically also councils say for a specific residential zone, we typically expect the roads to have this because they've obviously done research, extensive research. So if you have that, you can then just use your growth factor and then calculate your design traffic. And then now you have your CRB. If you have a CRB for 4 and your design traffic is, let's say, 1 times 10 to the power 7, and then you go there, and then you go, you're going to see that the thickness of the material, it's going to be 550, right? So now you know that your whole road needs to be 550 thick. So then now you now know your entire road thickness. Then you can say maybe my subgrade is going to be, my sub base is going to be 200, and my base is going to be 150, making 350, and then my actual surface course is going to be 200. Or you can make your base course 300 and you can make your base 200, and then you can have an asphalt layer of 50 mils at the top. It can be a chip seal or a double chip seal. People who practice in New Zealand or Australia will know what I'm talking about. But yeah, so this is how you go about it. And to find your California bearing ratio, you go on site and you do a DCP test. So first you calculate the cumulative depth of penetration in millimeters from each blow by adding the previous individual depth of penetration. Then you draw a chart using the data of the cumulative depth from the number of blows. Then, so the objective of that is to identify the different layers, right, that you're going to have as you go down. Then you identify the slope change of the penetration curve. So every change in slope shows that you're now in a different layer. Then after identifying each slope change, you calculate the average penetration for blow you calculate the average penetration per blow for each slope change and calculate the thickness of each layer. Then you use there's an equation that you use. I think it's logged. There's an equation that you use to find your CRB, and then once you use that equation, you can then find your CRB. But yeah, I'm sure this is something that you would have been taught in transportation engineering, because that's where I learned all that and I did it. It's also online. You can see, even on YouTube, it's there. You can just go have a look how to analyze DCP results, even how to do a DCP test. But I just thought I'd touch on it because it's something that I'm doing and it's something that I've done many times. So I just thought I'd run you guys through it. But yeah, so this is the design chart for the ASHTO design guidelines. So this design chart is assuming that it's a granular pavement with thin bitumen surface. So like I was saying, that 50 mil layer would then make sense. You can have it as a double chip seal with 50 mils. So you can have 50 mils for your surface course, and then you can have your base as 200, then maybe you can have your sub base as 300 to make up the 550. Then you're as good as gold. Yeah, so let's move on to the next. So our next we'll look at empirical design. So many pavement structure design procedures use an empirical approach. This means that the relationship between the design inputs, e.g. load, material layers, and configuration and environments, and pavement failure were determined using experience, experimentation, and a combination of both. Although the scientific basis for these relationships is not firmly established, they can be used with confidence as long as the limitations with such an approach are recognized. So specifically, it's not prudent to use the empirically derived relationships to describe phenomena that occur outside the range of the original data used to develop the relationship, but we still do it because it's the best method given the parameters that we have, or the parameters that you have in the situation. So now we'll move into the ASHTO method. So the reason why we're looking at the ASHTO method is because ASHTO is the mother of everything that we are doing here. So pavement, so the USA is the leading authority in pavement design. So ASHTO is extremely important, right? All guidelines, everything that we've been talking about from South Africa, New Zealand, Australia, everything comes from ASHTO. It comes from the ASHTO method, from these the study that was done in the 60s in America. Okay, so the most common empirical design method is that the one that was put forward in 1993 by the ASHTO guides, right, for designs of pavement structure. The equation relates pavement structures to applied load, surface life, the subgrade support, right, as measured by the resilience modulus. You can Google what that is. Okay, so the equation was developed from experimental data at the AASHO, or the ASHTO road test. This was like a $27 million road experiment, like in 1960. The road experiment was conducted in Ottawa, in Illinois, from 1956 to 1961. So that was a long time ago. So the ASHTO road test was a complex study of performance of highway pavement structures of known thickness under moving loads of known magnitude and frequency, and this was done by the Highway Research Board. Okay, so the test studies both Portland cement concrete and asphaltic concrete pavements, as well as certain types of short span bridges. So the resultant design equations are the popular method for pavement structural design. So those are the basis of this is all equations are derived from these experiments. Okay, so another common empirical design method was developed in California during the early 1940s by Francis Hevem, I don't know how to pronounce that, and others. This was referred to the California method. So this method was originally based on test track data from Brighton to Stockton in California, both near Sacramento. So similar to the ASHTO equation, the California method relates to pavement structure in the form of equivalent thickness of gravel to applied loads and subgrade support as measured by the R value. So when using the 1993 ASHTO guidelines, you have your GE, which is your gravel equivalent. I think we've spoken about that in depth. So this is the equation. So it's equals to 0.032 Ti. Ti is your traffic index or your ESAL per 1000. And that's a measurement of the pavement loading based on truck traffic. So it's based on the axles. So in South Africa, it would be 80 kilonewton axles. In New Zealand, it's a bit different. You can just look that up. I'm not trying to go into the technical aspects of all of this. That'll be in a separate course. But yeah, so all structural materials are expressed as an equivalent thickness of gravel, of course, because that's the methodology. And that's how you do it using whether empirically or for all the design guidelines, because the design guidelines are kind of empirical, but they're just a high level. There's a lot of abstraction. So they've removed a lot of the need for you to do the work. You don't have to find the equivalent gravel. They've already done all of that for you, and then you just pick depending on the traffic load that you get. And the R value is the underlying subgrade value. You'll also find this in South African guidelines. You'll find like the R value, and expert knowledge is required to use either the ASHTO empirical equations or the California bearing method. So a pavement designer should be consulted if you're considering using this. That would be me. So I feel like I'm an expert in pavement design, at least in terms of this. So you'd want to consult someone like me if I'm your senior at work, or if I'm a work colleague, or someone who would be 10 years, 15 years experience. When you do your design, just ask them to run to go through it, or you can run it by them so that you make sure that you're in the right direction. So yeah, I think that's all in terms of the ASHTO empirical equations. So moving on. So then we have the mechanistic empirical design method, right? So this is like the most advanced pavement structural design, uses, like the most advanced pavement structural design uses a mechanistic empirical approach. Unlike an empirical approach, a mechanistic approach seeks to explain the phenomenon only by reference to the physical causes. So it will look at like load repetition and how it will respond to deflection under various load repetitions. So in pavement design, the phenomena are the stresses, the strain, the deflection with the pavement structure. And the physical causes are loads and material properties of the pavement structure. The relationship between these phenomena and their physical causes is typically described using a mathematical model. Various mathematical models can be used, of course. Along with the mechanistic approach, empirical elements are used when defining the value of calculated stress, strains, and deflection results in the pavement failure. The relationship between the physical phenomena and the pavement failure is described by empirically derived equations that compute the number of loading cycles to failure. So like I was saying, we look at the number of repetitions or the number of cycles until it gets to failure. So yeah, that's typically how you carry out the mechanistic empirical. So looking at load failure would only just be mechanistic, but then when you look at the load failure using empirically derived equations, then it becomes mechanistic empirical. That's how the empirical comes in. So I hope I've touched on that and you kind of understand what I'm trying to get at. So the basic advantages of the mechanistic empirical pavement design method over a purely empirical one are, we'll touch on that on the next slide. So it can be used for both existing pavement rehabilitation and new pavement construction. So you can use it to rehabilitate your existing pavement, which typically happens now because I think most, like in the first world and in developed countries, they've already built most of the infrastructure. So now it's mostly just rehabilitation or upgrading. And you can also use it for new pavement construction, like here in New Zealand, they're still building a lot of roads. There's still a lot of infrastructure to be built. So you can use this method for construction of new roads. So it accommodates changing in load types. It can better characterize materials that are going to be used. It uses material properties that relate better to the actual pavement performance. It provides a more reliable performance predictions. It better defines the role of construction, and it accommodates the environmental and aging effects of the material, which is because you're going to be looking at cyclic loads. So a mechanistic empirical approach can also accurately characterize the in situ material, including the subgrade and the existing pavement structures. So this is typically done by using the portable device like a falling weight deflector to make an actual field deflection measurement of the pavement structure to be overlaid. So when you're, rehabilitating a road, then you can go with your falling weight deflector meter, and then you can drop it on the road and see how the existing road actually behaves, and you can use that data in your design. So these measurements can then be input into the equations to determine the existing pavement structural support and the approximate remaining pavement life. This allows for a more realistic design for the given conditions, of course. Again, expert knowledge is required when using the mechanistic empirical approaches. A pavement design expert should be consulted if you're considering to use it. Like I just said before, consult either an intermediate engineer like me at intermediate level, or a senior guy, or consult us both, because it's really important that you get it right.